Hi everyone, today we're going to be looking at vector multiplication. Our warm-up question deals with some information from previous lessons, so please just pause the video and try it out to start, and then we'll take it up. So now that you've tried this by yourself, we're just going to simplify these vector expressions. Remember, we talked before about how if the tip of one vector matches up with the same tail of the next vector, we can actually just simplify this as the tail of the first vector and the tip of the second vector. So this will be vector AB. We can also see this on our diagram over here. So if I have AE plus EB, the resultant of that vector addition is vector AB. So that should make sense. Okay, AE is actually equivalent to the vector EC. So for this one, I can write two things. I can either write 2AE, because we have two lengths of AE, or if I have AE and another length of AE, I basically have AC, that entire diagonal. So you can also write AC. For part C, I'm just going to start by rearranging some of these vectors and switching the negative vectors into their positive versions. And we can see here that this actually matches up nicely. So each of the tips and tails are all the same letters here. So we can express this as BC. Okay, same thing over here. Let's switch those negative vectors to positive vectors. And we can see that these are also matching up nicely. So the vector here would be AD. Okay, so getting into today's material, we're going to talk about multiplying a vector with a scalar quantity. So remember, scalars, they don't have direction, they only have magnitude. So we can multiply any vector by a scalar and it will alter the magnitude of the vector itself. It can also, if the scalar is negative, it can reverse the direction of the vector. So if we multiply a vector, let's say vector A, by a scalar, we'll call it k, we will have a new vector which will be the scalar k times vector A. The number k, which is the scalar, we call a scalar multiple. Okay, and k can be any real number, so literally anything that you can think of from negative infinity to positive infinity, decimals, 0, 1, fractions, whole numbers, negative numbers, roots, all of that kind of stuff can be used as a scalar multiple. So you'll see a bunch of examples over here of different scalar multiples and how they can impact your vector A here. Okay, so a couple examples of this first little scalar multiple rule is that if k is greater than 0, k is going to be in the same direction as our original vector A, and it's going to have a magnitude of the scalar k times the magnitude of A. So we can see here, this is probably a good example. If this is our vector A, if I do 2A, I'm going to have a vector that is in the same direction as A, which is twice the length of vector A. If k is less than 0, or in other words negative, the vector k times vector A will be in the opposite direction with a magnitude of k times the magnitude of A. So a good example of that are the vectors on the right of vector A here. So if I take vector A and let's say multiply it by negative 0.7, the vector will reverse directions and it will also become smaller because of that 0.7 multiple. Okay, this one is less than -1, or in other words, like it's going to cause a stretch to the vector. So the negative will reverse the direction, and then 21 over 10, or 2.1 times A, is going to make it about double the length plus an extra 0.1 there. I also mentioned above that your scalar can be any real number, which also includes 0. So if k happens to equal 0, the result will be the 0 vector. All right, so we have an airplane heading due north at 100 kilometers per hour. The airplane's velocity is represented by vector v below. Draw the vectors negative b, half v, and negative half v. Give an interpretation for each. Okay, so negative v is pretty straightforward. We're just going to take v, reverse its direction, and there's our vector negative v. This means that we are going 100 kilometers per hour in the opposite direction to north, which would be south. Okay, half v. So this is going to be going in the same direction as v, and it needs to be about half the length. So half of that vector's magnitude, so if the magnitude is represented by 1,000 kilometers per hour, half of that is actually going to be 500 kilometers per hour in the same direction as the original vector, which will be north. Okay, and then negative half v is basically the same vector that we just drew, but in the opposite direction, which makes this 500 kilometers per hour in the opposite direction of north, which would be south. Okay, you'll also notice with my vectors, the vector symbol only goes over the vector itself. It doesn't go over the scalar. Okay, so we have a vector u, which is shown in two of our diagrams below. The magnitude of vector u is 100 kilometers per hour, and its bearing is north 40 degrees east. We're going to draw a vector with each scalar multiplication, and also describe the resulting vector. So for 3 times vector u, I want 3 lengths of vector u in the same direction, and the resulting vector is basically going to be the single vector that extends through that length. So just so we can see it a little bit better here, thicken it up. So this is our vector 3u. And the description of our vector, it's going to be 3 times the magnitude, so 300 kilometers per hour. And the direction will remain intact, so north 40 degrees east. Okay, for our second one, I didn't want to draw the scale of this one on here, but we're just going to use our picture from over here to get something half the length of u. So 0.5 u, we want it to maintain the direction there, but draw it half its length. So about this. Okay, so if we've halved the magnitude, this now means that we are going 50 kilometers per hour, and the direction remains the same, north 40 degrees east. And then for our last one, negative 2u, so we want 2 lengths of u, but in the opposite direction. So that's about 1 there, and 2. So the full vector that extends that entire length is the vector negative 2u. So that's our vector, negative 2u there. So we are doubling the magnitude, so this is going to be 200 kilometers per hour. And we're reversing the direction. So if we think about the opposite angle theorem, it says that opposite angles are equal, so that makes this 40 degrees as well. So we can say south 40 degrees west for the direction. So we've discussed parallel vectors before, and 2 vectors that are parallel, we use the word collinear to describe them. So basically what we're saying is that they can be translated to be on the same straight line and are therefore scalar multiples of one another. So that means that if we say a vector is collinear with another vector, we can assume that the vectors are scalar multiples. I also introduced some properties for addition and subtraction. There are properties for scalar multiplication as well. So the first one is the distributive property. And this tells us essentially we can do distributive property as we normally do with a scalar in front of a vector addition or subtraction. So distributive property works the same way as usual. Associative property basically just says I can either multiply the scalars together and then multiply by the vector, or I can multiply one of the scalars by the vector and then multiply by the other scalar after that. So it doesn't matter the order in which we do multiplication by multiple scalars. And then the last one, the identity property, basically just says if I multiply a vector by a scalar of 1, I get back that same vector itself. So pretty similar to the mathematical laws that you already know. Okay, so we've got a couple expressions for vectors x, y, and z here, and we're just going to determine each of the following expressions, a, b, and c, in terms of I, j, and k. So for x plus y, we're just going to sub in the expression for x and the expression for y. And we can gather vectors the same way that we gather variables. So if I have negative 4j plus j, it will give me negative 3j. And same thing with the k's here. So k minus vector 1 vector k minus 5 vector k is going to give us negative 4 vector k. And again, remember your vector symbol should only be over the actual vector. The scalar should not have a vector symbol over it. Okay, so similarly here, we're just going to copy out the expression for x. And we want to subtract that by the y expression. And here we're using the distributive property rule. So if we imagine that there's a negative 1 here, we're just distributing that scalar of negative 1 into the bracket. Okay, and then we can gather as usual. So the mathematical laws and rules that you know and you've been learning through your math travels, they haven't changed. They're the same with vectors. Okay, and then for the last one, we'll just copy out the expressions here quickly. Okay, I see a lot of students when they are working with vectors, they don't write their vector symbols. You need to write your vector symbols. I know it can be a little bit tedious, but we are working with vectors, so please make sure that you're writing those symbols on top with every line that you do. Okay, and then you're just going to gather up your common vectors here. So 3i minus 3i is actually going to result in 0 vector. So we should just be left with j's and k's after this. So we've got negative 9 j's, or times vector j, I should say. And we have 23 times vector k. A linear combination is created when we are adding 2 or more vectors that have scalar multiples. So you may see that word come up in some questions. You'll see it in the next question. Basically, it just means like a combination of vectors with scalars. Oops. Okay, so we've got a trapezoid A, B, C, D. It tells us that the line segment BC is parallel to the line segment AD, and that the line segment AD is 3 times the length of the line segment BC. So here you'll notice I don't have any vector symbols, and that's simply because we're just referring to the line segment from A to D and B to C. Now if we translate those into vectors, so we give them a direction, we know that vector AB is equal to U, so that's shown in our diagram, and vector BC is equal to V. So we're tasked with finding AD, BD, and CD as linear combinations of U and V. Okay, so the vector AD. So here's your vector AD. And what we do know about the line segment AD is that it's 3 times the length of the line segment from B to C. So if we know that BC equals V, I must know that this line segment, or that this vector from A to D, is 3 times vector V. So in this direction, from A to D, we know this is 3V. I'm just going to keep that labeled here for our next questions. Okay, BD. Here's BD. I think we can probably write this as a combination starting from B going to A, and then from A to D. So if I try to use BA plus AD, I know that AB is positive U, so BA must be U but in the opposite direction, so negative U. And we know that AD from our previous part is 3 times vector V. Okay, and I'm actually just going to leave that line here because CD, if I wanted to express CD as a combination of other vectors, probably well, I guess we could do this a couple ways. Let's say we erase this. We can get from C to D, starting at C. I'll just do this in pink here. We'll start at C, we'll go to B, then we'll go from B to A, and then A to D. So I'm going the opposite direction of vector V, the opposite direction of vector U, and the same direction as vector V here. So we should get 2V minus U. All right, the last part of our lesson is explaining what a unit vector is, and then we're going to do one last example. So if we take any non-zero vector, let's say vector x for example, and multiply it by the scalar 1 divided by its own magnitude, so 1 divided by the magnitude of x, and we multiply x by that scalar, we're going to get the vector that has the scalar 1 over the magnitude of vector x times vector x. And this will be the vector that's in the same direction as x, but it has a length of 1. So you can see a picture over to the right of kind of what I'm talking about here. So if we have a vector x with magnitude 3, 1/3 of x is actually going to have a length of 1. We're going to see unit vectors come up a little bit more when we do some application questions, so that's kind of where you'll see them come into play. All right, so let's take a look at a sample here. We have vector u with a magnitude of 4, vector v with a magnitude of 5, and we know that the angle between these vectors is 120 degrees. Determine the unit vector in the same direction as u plus v. Okay, so here's what we know. One little reminder that we talked about in a previous lesson is that when we describe the angle between vectors, this is the angle when the vectors are arranged tail to tail. So we don't really know the orientation of these in space, kind of meaning like we don't know where they're rotated, but we do know if I draw a vector v out here, and let's say that that vector is 5 units in length, if I make sure that that vector u is about 120 degrees, and I probably should have drawn it a little bit longer, needs to be close to the length of v, but a little bit shorter. So you guys, if you have a ruler, you can actually draw this to scale. So let's say maybe you make 1 centimeter, like just do it with centimeters, and then make u 4 centimeters and v 5 centimeters. If you have a protractor, even better, because then you can actually measure out 120 degrees and you can have like a perfect scale model of what we're talking about here. So we're going to use parallelogram method that we talked about for adding vectors. And parallelogram method basically works when we have two vectors arranged tail to tail. And the vector that starts where their tails meet and ends at the opposite diagonal is the resultant of u plus v. Okay, we also mentioned in a previous lesson that when I have two parallel vectors, like this is u on one side and vector u on the other side, they form a C pattern and the interior angles add to 180. So I can actually figure out the angle over on this side as well, just by subtracting from 180. So this will be 60. So I know that this has a length of 5. And I know that this is opposite to vector u right here, so that has a length of 4. So our goal here is to find the magnitude of u plus v. And I have two sides with a contained angle here, so I'm going to use cosine law in order to do that. So we're going to square the two sides. And then subtract 2 times the two sides times the cos of the contained angle. You guys can take a second and pause the video, sub that into your calculator. So you should have got 21, and then I'm going to get rid of that squared by just square rooting here. So this is the magnitude of u plus v. So if I want to find the unit vector that's in the same direction as v plus u, basically what the above instructions are saying is that I will do 1 over the magnitude of the vector times the vector, and this will give me the vector that has length 1 in the same direction as the vector that I'm multiplying it by. So we're going to take, to create our unit vector, we're going to take 1 over the magnitude of u plus v and simply multiply that by vector u plus v. So we found the magnitude as root 21 above. So we can write it like this. And if we wanted to rationalize the denominator, we could also write this as root 21 over 21.